What's the link between dirt and the cure for one of the most common and deadly human diseases? Alongside this, have you heard of the controversy linking these two? If you wish to find out more, stay tuned. Welcome to the Drug History Podcast. In this episode, we're looking at the fascinating story of the discovery of aminoglycosides. Aminoglycosides are a group of antibiotics that include neomycin, kanamycin, tobramycin, gentamicin, cisomycin, amikacin, netomycin, abacacin, and plazomycin. In the UK, only amikacin, gentamicin, neomycin sulfate, streptomycin, and tobramycin are used. They are a useful group with antibacterial properties against some gram-positive and many gram-negative organisms. As such, they are used in serious infections, including but not limited to tuberculosis and endocarditis. They are not absorbed from the gut and must therefore be given by injection for systemic infections. What we want to look at in this episode is how we came to use the aminoglycosides in the first place. The history is by no means straightforward. The sanitized version of the story is benign enough. A 2008 article in the American Society of Microbiology journal gives a brief summary of the history of aminoglycosides as follows. Aminoglycoside antimicrobials were first discovered in the 1940s and originally isolated from actinomycetes. Streptomycin, isolated from Streptomyces griseus, was the first aminoglycoside introduced into clinical practice for the treatment of tuberculosis. Waksman, the first to coin the term antibiotic, won the Nobel Prize in 1952 for the discovery of streptomycin, along with Albert Schatz, who was eventually recognized as a core discovery. Naturally, this should raise questions regarding why Waksman appears to have gained immediate recognition for the discovery, while Schatz was only recognized some time afterwards. There is some debate among fans of either scientist over who should get credit for the discovery of streptomycin. Let's start off by looking at the arguments for granting Waksman the honor just by himself. According to Boyd Woodruff, who studied under Waksman as a PhD student from 1939 until 1942, Waksman deserves the credit for several reasons. Firstly, Dr. Waksman had developed a technique for the large-scale production of streptomycin based on other antibiotic manufacturing techniques, thus enabling rapid animal testing and human trials with Mycobacterium tuberculosis. Secondly, although streptomycin was discovered from actinomyces bacteria, it had to be shown to be distinctly different from the natural product in order to be patentable. Waksman showed that crystalline and highly concentrated products differed appreciably from the natural soil products, thereby opening the door for patents on hundreds of new discoveries by others. Thirdly, he had created the new genus name Streptomyces, and with his friend Arthur T. Henrici, realigned the Actinomycete taxonomy. Fourth, he had led his department in finding various new drugs, with the methods used being copied later by dozens of commercial organizations. Among other historical points of interest raised by Woodruff are the following. Firstly, that Waksman had a long history in the investigation of the bacterial properties of certain soil bacteria. In fact, as early as 1923, when the Western scientific and medical world was still only coming to understand microbes, Dr. Waksman and a student, Robert Starkey, were the first to make the discovery of the bactericidal properties of actinomycetes soil bacteria. Dr. Waksman was a microbiologist working extensively in soil microbiology at the time. He soon became the preeminent expert on soil microbiology. We also hear that in 1937, Dr. Waksman had a sudden realization that he needed to investigate in further detail the discovery from 1923. This had to be done scientifically. He assigned two of his best PhD students to do this, and they published their findings alongside Dr. Waksman's historical report later the same year. While Woodruff does not identify what triggered this sudden realization on the part of Dr. Waksman, a 2002 article in The Guardian suggests that this renewed interest was triggered by news that a team at Oxford University had managed to purify penicillin. The third background information that we learn is that Waksman then shifted his interest from soil microbiology in general to antibiotic studies. He gathered a further group of 8 researchers, all working towards their PhDs between 1939 and 1943 to research antibiotics. They discovered several antibiotics including actinomycin, streptomycin, fumigacin, and clavicin. These were found to be toxic to animals. Finally, towards the end of that period, Albert Schatz was added to the team. We allow Woodruff to carry on the narrative at this point. He says, in the final portion of that 5-year period, Albert Schatz, the most recent PhD student joining our group to search for antibiotics, arrived and started his research under Dr. Waksman. Then he was drafted into the army. After a few months, he was released and was able to return and actively search for a useful antibiotic, again under the direction of Dr. Waksman. In his 11th consecutive soil plating, each of which required less than a week's time, including checking for the presence of an antibiotic, he isolated a Streptomycin griseus strain from the farm soil of the Rutgers Agriculture School. That strain produced an antibiotic. The culture differed little from Dr. Waksman's many prior Actomycetes griseus isolations made over his many years of research, but the presence of an antibiotic was new. Dr. Waksman and his student Schatz named it Streptomycin. A sample was given by Dr. Waksman to the Mayo Clinic's expert researchers, Drs. William Feldman and Colin Hinshaw, who were specialists in tuberculosis studies, and after testing it, they reported that it was not toxic to various animals. It was the first Rutgers antibiotic obtained that was not toxic to animals. Therefore, Schatz's culture was a very significant discovery. Now, Woodruff therefore argues that Waksman was the overseer, guiding and refining the research process over many years, while Schatz happens to have been the lucky student who turned up at the end of the process and stumbled upon the right results after many years of hard work by others. On the other hand, the defenders of Albert Schatz paint a picture of a brilliant researcher who brought clarity to the somewhat unsuccessful efforts of Salman Waksman over many years. Michael Rollins, writing in The Lancet in 2012, references the research of Peter Pringle into the alleged unprofessional behavior of Waksman in seeking to diminish the contributions of Schatz, denying him a rightful share of the Nobel Prize and subsequently destroying his career. This is detailed in the book Experiment 11. Michael Rollins summarizes Peter Pringle's findings as follows. He says, Peter Pringle, in Experiment 11, chronicles the discovery of streptomycin by Albert Schatz while working in Waksman's laboratory at Rutgers University in New Jersey. Waksman was primarily a soil microbiologist and a world authority on Actinomycetes species. During the late 1930s, and trying to emulate Alexander Fleming's discovery of penicillin, Waksman set about attempting to identify, with help from the nearby Mac laboratories, antimicrobial agents produced by microorganisms in soil that, unlike penicillin, would be active against gram-negative organisms. Waksman had some early successes with actinomycin and streptomycin, but these proved too toxic for use in man. Then, in 1943, Schatz, a newly arrived graduate student, found that an agent produced by 2 strains of Actinomyces griseus was active against Escherichia coli. It was the 11th of the experiments that he undertook to find an antibiotic against gram-negative organisms. A little later, Schatz showed it had antimicrobial activity against a range of other gram-negative organisms, as well as non-virulent and virulent strains of Mycobacterium tuberculosis. Schatz had discovered streptomycin. The 2002 Guardian article quoted earlier adds some details from this perspective. Talking of Albert Schatz, it says, in 1942 he began work for his PhD under Waksman's supervision, and the two soon became close. The professor was impressed by his young pupil's sharp mind and dedication. On more than one occasion, he referred to Schatz as the most brilliant student I have ever had. Schatz, in turn, admired and respected his professor. He was my mentor, says Schatz. 5 months later, Schatz was drafted into the army. As a bacteriologist at a Florida military hospital, he witnessed firsthand the failure of penicillin and sulfur drugs against certain bacterial infections, called gram-negatives, and against TB in particular. He says, I saw servicemen dying of these infections. They were men my own age. I got to know them, he says. He began to devote all his spare time to the search for a new, more effective antibiotic. After being discharged because of a bad back, Schatz returned to Rogers, where he asked to be allowed to continue his search for an antibiotic that would be effective against gram-negative bacteria as well as TB. Waksman agreed, but because his student would be working with the virulent tubercle bacillus, which causes the disease, relegated him to the basement and never visited him there. Schatz threw himself into his research, testing hundreds of different colonies of Actinomycetes. I generally began my work between 5 and 6 in the morning and continued until midnight or even later. I was isolating and testing everything I could find. The young researcher often ate in the lab, vegetables, fruit, dairy products donated by colleagues in other departments, and sometimes even slept there on a bench because he was too tired to go home. And home was a room in a greenhouse in the plant pathology department, where he lived rent-free in exchange for maintenance work. He worked hard, partly because, with a stipend of $40 a month, he couldn't afford a social life, but also because he felt an overwhelming compulsion to find an effective antibiotic. When I was a boy, I knew children at school and neighbors who had tuberculosis. I saw them lose weight and waste away. None of them could afford to go to a sanatorium, so they remained home, coughed, and infected others. After just 3.5 months, and against all the odds, Schatz's hard work paid off. He isolated not one, but 2 highly active strains of Actinomycetes, subsequently renamed Streptomyces griseus, which stopped the growth of several virulent bacteria known to resist penicillin, including the dreaded tubercle bacillus. One strain had come from heavily manured field soil, the other from a swab from the throat of a healthy chicken, which Ralston had passed him through the basement window after she had finished working with it. On October 19, 1943, at about 2 p.m., I realized I had a new antibiotic, says Schatz. I named it Streptomycin. I sealed the test tube by heating the open end and twisting the soft, hot glass. I first gave it to my mother, but it is now at the Smithsonian Institution. I felt elated and very tired, but I had no idea whether the new antibiotic would be effective in treating people. We note that the Guardian article indicates that Schatz was left to work by himself in the basement, without effective supervision, while at the same time being heaped with praise, due to the dangers associated with Mycobacterium tuberculosis. It goes on to say that after the discovery of streptomycin, Waksman began to participate actively in the research. At this point, we go back to the Lancet article. It says, Schatz prepared sufficient material for its activity against tuberculosis to be investigated in guinea pigs, and then in a few patients, by William Feldman and Colin Hinshaw at the Mayo Clinic. Scientists at the Mac laboratories, close to Rogers, oversaw the subsequent development of streptomycin. In the two major publications on streptomycin that followed, Schatz was the first author, and he and Waksman were jointly granted a patent for streptomycin. That was the high point of Schatz's career. 2 years after the discovery of streptomycin, Waksman bullied Schatz into assigning his share of the rights to streptomycin to Rogers University. Waksman stated that he had already done so, and that if Schatz declined, he would use his influence to kill job chances. What Waksman failed to mention was that he had made a deal with Rogers to receive 20% of the net royalties. His royalty payment for 1948 alone was $124,000. Schatz only discovered of the deal in 1949 and sued Waksman for his share. Waksman eventually made an out-of-court settlement. In the meantime, Waksman successfully attempted to diminish the contributions that Schatz and others had made in discovering streptomycin. The reason behind this was the desire by both Waksman and his university for him to be awarded a Nobel Prize. In doing so, there was a major problem. Nobel Prizes, under the terms of Alfred Nobel's will, can only be shared by a maximum of 3 people. The discovery and development of streptomycin, however, not only involved Waksman, but potentially the other authors of the 2 original scientific papers, as well as the Mayo Clinic investigators and scientists at Mac. Waksman, ably assisted by the Rogers Public Relations Department, successfully set about minimizing the contributions of Schatz and the other collaborators. In October 1952, the Nobel Assembly announced the award of that year's Nobel Prize to Waksman alone for the discovery and omitting the word development of streptomycin. Appeals by Schatz and his friends were of no avail. Schatz's experiments were not the first time a postgraduate student had been excluded from a Nobel Prize. Charles Best was excluded from the Nobel Prize awarded in 1923 to Frederick Banting and John MacLeod for their discovery of insulin. Banting was so outraged that he gave half his share of the prize money to Best. Best went on to have a distinguished career, but Schatz was not so lucky. Because of his ill-deserved reputation as a troublemaker, Schatz was never able to find employment as an independent scientist. He died in 2005, an embittered old man. Dr. Woodruff's account provides alternative explanations for some of the points raised by the Lancet and Guardian articles. Regarding the fact that Schatz worked alone in the basement, Woodruff recalls a conversation with Waksman that included a discussion of this. He says, on one occasion, he told me he had enjoyed working at the laboratory bench with me for a year because our target, the killing of gram-negative E. coli cells, was research-based. However, after his student Schatz had replaced that approach with his routine soil blatings, Dr. Waksman said he felt it was no longer a true research project, just screening, so he could not bring himself to work with Schatz at his basement laboratory bench to help broaden his studies. But, in fact, Waksman had become greatly concerned. He felt his failure to work with Schatz in his basement laboratory several years in the past had led to some complications that had developed between them. On the matter of the final arrangements that became the subject of the lawsuit, Woodruff's understanding is presented as follows. The complications between Dr. Waksman and Dr. Schatz, after the latter had graduated, became truly serious. The distribution of royalties on the sale of streptomycin had not been clearly defined and became altered as time went by. 80% of the funds were set aside for the construction of a new microbiological research program at Rutgers Bush campus, which had become the center for the university's scientific programs. Dr. Waksman accepted rights for the 20% royalty remainder, primarily to expand research on streptomycin beyond the scope of Rutgers University. He felt strongly that it was necessary to do so for any patented discovery made in a university. He spent the funds on purchases of streptomycin, and he supported studies on it by other universities and other established research programs. Later, a change in royalty distribution was introduced, such that Dr. Waksman should receive some royalty funds as a salary to add to his university income because it was taking so much of his working time. Dr. Waksman was absolutely shocked when a legal suit was filed by Dr. Schatz against him and the university, especially after Dr. Schatz, as a postdoctoral scientist, had obtained several research positions based on Dr. Waksman's recommendations. The university management had adopted a procedure by a vote, accepted by Dr. Waksman, that the royalty funds should be directed to the university laboratory where the discovery had been achieved, that is, the soil microbiology department of the agricultural college. The legal suit therefore became a severe concern for Dr. Waksman. The case, however, was eventually settled before going to court. Dr. Schatz accepted a proposal put forward by Dr. Waksman, although not pre-approved officially by the legal staff. Dr. Waksman decided that if he were to receive royalties as salary, similar gifts should be passed to students and laboratory employees who had been involved with streptomycin. He proposed that 10% of the royalties should be passed to them, 26 persons in all, the majority as lump sums and other portions as percentages for the remaining royalty period, with Dr. Schatz, as discoverer of the streptomycin-producing culture, receiving the largest fraction. Dr. Schatz accepted the proposal. This settlement restored somewhat the relationship between Dr. Schatz and Rutgers University. Several important awards, including the Rutgers Medal, were given to him by Rutgers University's top management. Also, some lectures by Dr. Schatz were presented in Rutgers facilities during the 50th anniversary of the discovery of streptomycin. Later, Rutgers Agriculture School students insisted that a plaque showing that Albert Schatz was truly a co-discoverer of streptomycin must be placed in the building where streptomycin had been discovered, and this was done. However, this favorable presentation of Dr. Waksman is not supported by other sources. The Guardian notes that, and I quote, "And so, on December 12, 1952, Waksman was awarded the Nobel Prize. Professor A. Wahlgren of the Swedish Caroline Institute tried to diffuse the tension by declaring that Waksman had been awarded the prize for his ingenious, systematic, and successful studies of the soil microbes that led to the discovery of streptomycin, instead of simply saying for the discovery of streptomycin as had first been announced. In his acceptance speech, Waksman did not once mention Schatz, using the royal we instead. Nor is there any reference to Schatz in Waksman's 1958 memoir, My Life with the Microbes. He is named only as the graduate student. The Guardian article goes on to highlight that after being awarded the Nobel, Waksman went on to oversee the production of many other life-saving antibiotics, co-authored 500 scientific papers, and wrote or edited some 28 books. He died in 1973 at the age of 85, widely regarded as the father of antibiotics. Schatz never again worked in a first-class microbiology lab, but managed to make some important contributions to fields as diverse as science education, nutrition, pollution, and water fluoridation. In the early 1960s, unable to find work in the US, he took his family to South America, where he worked as a professor at the University of Chile, while Vivian, his wife, was director of the US school in Santiago. In reference to the decision by Rutgers University to award Schatz the Rutgers Medal, this was not down to Waksman or the original university authorities at all. It was, rather, due to the work of another Milton Wainwright of Sheffield University many years later, in the 1990s. It happened more than 20 years after the death of Waksman. This is how it happened. Schatz's contribution to the field of antibiotics might not have gone unnoticed altogether if it hadn't been for Milton Wainwright at Sheffield University. Researching the history of streptomycin, he went to Rutgers to look into the archives. He was puzzled by what he found. Why hadn't he heard of this Albert Schatz? He decided to investigate, studying all the scientific papers and legal documents, interviewing former staff and students, and meeting Schatz himself. As soil microbiologist himself, he understood exactly the steps involved in Schatz's research. I was totally confident that he discovered streptomycin alone. I felt very emotional because I could feel he had been gravely wronged, says Wainwright, over coffee in a Sheffield diner. He wrote a few articles in scientific journals about his findings and included Schatz's story in his book on antibiotics, but failed to generate much support within the scientific community. Wainwright's visit, however, had intrigued professors at Rutgers. They decided to meet with Schatz and, finally convinced that he had been the victim of a grave injustice, began to lobby for his rehabilitation. On April 28, 1994, the 50th anniversary of the discovery of streptomycin, Albert Schatz, then 74, was awarded the Rutgers Medal, the university's highest accolade. Many others have since recognized his role as well. The various accounts we have referred to suffer from some weaknesses. Woodruff's account, while based on his own interaction with Waksman both as a student and in years afterwards, lacks the balance that might have been brought by a similar level of interaction with Schatz. It is possible that Woodruff might himself have retained an unconscious bias against Schatz, since Schatz had achieved success where Woodruff had not. Woodruff discovered streptomycin, which proved toxic to animals and humans, while Schatz discovered streptomycin, the drug that was the basis for the 1952 Nobel Prize for Physiology or Medicine. Similarly, the versions presented by The Lancet, Peter Pringle in Experiment 11, and The Guardian were written many years after Waksman's death. As such, they do not include a response from Waksman to some of the more grievous accusations. In the ideal world, all the interested parties would have been invited to a fair hearing and given equal opportunities to make their cases. However, there appears to be enough evidence of a smoking gun to warrant the questioning of the traditional version of the discovery of streptomycin that was for many years regarded as correct. And so, as we look back at the story of the discovery of streptomycin, which was the first of the family of antibiotics referred to as aminoglycosides, we find that there was enough real-life intrigue and acrimony to match a best-selling fictional bestseller. At the same time, the experience offers medical researchers lessons on how to conduct collaborative research and on the need for educational supervisors to recognize the contributions made by their students. Thanks for joining us for this episode of the Drug History Podcast.